Welcome everybody to this afternoon's session on innovations in the electromagnetic spectrum and to include electromagnetic spectrum sharing. I'm Bob Schneider with the Defense Spectrum Organization. I'm the tech director here, and I'm joined by a number of my colleagues from the Defense Spectrum Organization who will be presenting on different aspects this afternoon. All right, so here is the standard disclaimer slide. I won't read this to you. I'll let you read it yourself. All right, so let's go ahead and move on to the content and the briefing. Once again, welcome everybody. What we're going to be talking about is the electromagnetic spectrum and our plans to achieve electromagnetic spectrum maneuver in this area. So just a few words about the electromagnetic spectrum. Every single system that we have on the battlefield, everything that the Department of Defense uses, is reliant upon access to the electromagnetic spectrum. Think about flying an aircraft to maintain connectivity, to sense, to communicate, etc. We're doing that on the fly, and we're doing that via wireless means or via the electromagnetic spectrum. The same is true for every single military platform that we have out there on the battlefield today. You're not going to see a roll of fiber optic cable being strung behind that platform as they fly, as they move, as they maneuver out there in the deep blue sea. It's all via wireless means. Today's electromagnetic spectrum on the battlefield has three characteristics, the big C's, if you will. The spectrum is congested, it is contested, and it is constrained. From a congestion standpoint, it just means that there are a lot of users of the electromagnetic spectrum. It's very crowded. If you will, think about being on the Washington Beltway at rush hour. That's congestion. We're seeing the same thing in the electromagnetic spectrum. Contested refers to the fact that we are dealing with adversaries. Those adversaries get a vote in terms of how the spectrum is being used to include potentially jamming our assets on the battlefield. Constrained has to do with regulatory policy constraints on how we access, how we use the spectrum, both domestically as well as at locations overseas. Maneuver is required in the electromagnetic spectrum. Every single domain out there has maneuver as one of their principles, as one of the things that needs to be done in order to conduct military operations. The same is true in the electromagnetic spectrum. If you will, think about, once again, the analogy of driving on the Beltway, the Washington Beltway in rush hour. If a car next to you starts to drift into your lane, obviously you want the ability to maneuver to get out of the way. We need the same thing in the electromagnetic spectrum. So some may ask, why do we need innovation in the electromagnetic spectrum? For the most part, spectrum management has been a reservation-based type of model for many, many years. That served us quite well when spectrum was very plentiful. But now, because it's congested, contested, and constrained, we need the ability to maneuver, and we need innovation to do that. And what you see is a number of areas across the bottom of the slide, going from EMS situational awareness all the way to EMS sharing on the lower right-hand side, and we need innovation in each one of those areas. What you will get this afternoon is a number of briefings talking about innovations in each one of these areas. First up, Greg Wagner talking about transformations in spectrum sharing. Next up will be Stuart Schutta talking about EMS algorithm innovations. Next, Betsy Park talking about big data analytic techniques and how that's helping us deal with EMS data. Rocksvold will talk to us about spectrum visualization and how we're doing that. And then to wrap us up, Howard McDonald will talk about innovation in spectrum sharing to help us deal with a number of challenges in a particular spectrum band. We're going to hold all of the questions until the last 10 minutes. We'll open up the mics at that point for questions. And if you do have a question at that point, please go to the microphone. Everything's being recorded, so in order for your question to be heard by all as well as to be recorded, please use the microphone. So with that, I'm going to turn things over to Greg.
Thanks, Bob. So I wanted to start first by kind of talking a little bit about why we're talking about spectrum sharing. In 2013, the department published a spectrum strategy, and part of that spectrum strategy was to engage in spectrum sharing as a way to increase the Department of Defense's access to spectrum. As Bob kind of did a real good job of setting the stage for why we need that access to spectrum. But it is a constrained environment, and spectrum sharing as a strategic goal was a way, and still is a way, for the department to gain and maintain that access. But also, in terms of the warfighting dimension, which is, of course, what the Department of Defense does, there's a term called cooperative spectrum use that's used in the warfighting community, which means the same thing. How do we continue to use the spectrum when others are using that same spectrum, seek to constrain our use of that spectrum, or seek to deny our use of that spectrum? Now, the interesting thing about spectrum sharing is we've been doing it for a very long time. It's just that the doing of it has been reservation-based, as Bob mentioned. It has been on time scales that are kind of calendar-based, very manual processes. And now we're seeing technology coming into the physical layer of the OSI stack that is allowing us to make rapid movements in spectrum, and we don't have the attending infrastructure or ecosystems to address that. Now, I have a picture up there of the 3.5 gigahertz ecosystem that's in use today, and this is an exemplar of one of the types of ways that spectrum sharing could be done today. This is an excellent opportunity for innovation. The demand signal is that we're going to have to do more and more of this. And we need to drive the time scales from the manual to the automated, from the calendar to the machine. And this is one of the reasons that we're here talking to you today about spectrum sharing, and what are those transformations that we need to make, or that are being made by the market today, that we're going to have to adapt to. And so that's my next slide, and I hope to set the context for the following speakers by going through some of these things. So yesterday we had human-based sharing. Today we have bolt-on type of systems. So these are additive ecosystem type of things that are added to current operations. And tomorrow we believe the demand signal is these will be device-based and from calendar to machine time scales. So faster than human cognition, certainly faster than human decision making. An interesting part of this is the demand signal that we're sensing on data and analytical capabilities. And you're going to hear a lot about that later today. So the data that we needed yesterday to do spectrum sharing isn't the data that we're going to need tomorrow to do spectrum sharing. So we have a data challenge, and for those of you that were at today's lunchtime, heard the panel discussion from Joint Force Headquarters, Doden, they're sensing those same demand signals. The J2 talked a lot about the need for data, big data, data analytics, and we perceive the same thing in this space. And our techniques have to change. Basic techniques, manual type techniques, going more toward automated techniques, statistical techniques for assessing whether or not spectrum can be shared and for how long. And this kind of takes us from a simple space through a complicated space to a complex space. And that transformation, those last two transformations from complicated to complex have some profound meaning. And I think a lot of the folks in the IT community today understand what that means in terms of cause and effect behaviors and being able to navigate through those spaces. Very, very difficult and not a space that we have experienced up to now in the spectrum world. And all of this, again, driving to gaining and maintaining that spectrum access that in turn allows the department to be more lethal in the application of its kinetic and non-kinetic effects. So with that, I will turn it over to Stuart, who will talk about some of the algorithmic innovations, and then followed by Betsy and Rocky, who will talk about some of the data innovations, and then Howard will share with you an exemplar of some of the dynamic spectrum sharing scenarios that we have in store for you.
Thanks, Stuart. Thank you, Greg. A key enabler of spectrum sharing is being able to understand the consequences of interference among different spectrum using systems. Now, a lot goes into building that understanding. You need data, you need visualizations, you need automation, and you'll get to hear a little bit more about those as we go along. But between the data, the raw data, and those higher level visualizations, automation, you need algorithms. You need something that's going to turn the raw data into actionable information that you can use to make decisions. Now, DSO has a number of efforts in progress to innovate and create new algorithms to help us do that. I'm going to talk about one specific example for analyzing interference in the aggregate. So what do I mean? What do I mean by that? So in spectrum sharing, specifically spectrum sharing in the 1755 to 1780 megahertz band as DoD relocates their systems, we have a situation where there are thousands and thousands of cell phones transmitting and DoD systems that are being impacted by those transmissions. Now, existing algorithms that we had going into this to do these analyses were either very conservative, doing worst case analysis, or they were very slow. They generated statistics by doing thousands upon thousands of simulations of a single scenario to come up with the statistics that could feed into those decisions. So as we went into this, DSO innovated and developed a new algorithm for directly coming up with the statistics of this aggregate interference so that we could make those decisions and share spectrum. Now, part of this algorithm is improved models that help us understand the impacts of environmental features like buildings and trees and the statistics there, models of the individual cell phones, their statistics, and how they operate in different situations, different environments, different times of day. And our algorithm uses advanced principles from statistics to take all that raw statistical information, combine it together, and give us resulting statistical distributions from which we can make risk-based decisions with regard to spectrum sharing, how we use the spectrum, and how we share with these cellular systems. So where are we going with this? With this algorithm giving us higher fidelity views into the impacts interference is having on our systems, we're looking at how to expand this beyond just the spectrum sharing scenario, where we've had great success thus far, and we're looking at how to apply it in other scenarios for warfighting and EMS maneuver. So as part of that future, we would be looking at how to bring in more statistics, so modeling other aspects of the environment, of the systems in that environment, collecting statistics for those, expanding out the algorithm to take these into account, to deliver solutions and answers and actionable information faster than we've been able to do before. Thank you. Betsy?
Oh, there we go. So as Bob mentioned, almost every DoD system has some degree of dependence on the spectrum. And so it's increasingly important for the warfighter to be able to optimize his use of the spectrum. And due to the quantity and increasing quantity and complexity of that data, it's going to be critical for us to be able to apply big data analytics to this domain. So what is our data? What is the spectrum data? We run the gamut from highly specified measured data to documentation. So first and foremost is our beloved regulatory data. Documentation that defines the operating parameters and constraints of our systems. This includes the frequency assignments, which are basically reservations in the spectrum for a given system in a given location. Equipment characteristics, which are approved as a result of spectrum certification process. We are also interested in adversary system characteristics as well. We need real-time position information, emitter location, and as Stuart talked about, interference is one of our major concerns. So we need to know the time and place that interference occurs, and this is really a ripe area for application of analytics to be able to predict and assess whether interference is intentional or unintentional. We have modeling and simulation data, which would consist of very detailed antenna patterns and propagation loss overlays, contours, given terrain and given urban environments. We also have environmental data, so this would be atmospheric and weather conditions that impact the spectrum, space weather, ionospheric conditions, sunspots, etc. And of course, an increasing interest and need to be looking at spectrum monitoring data. This is data collected by sensors, real-time data. And lastly, because command and control and electronic warfare are major activities in the spectrum, we need to understand their planning and obtain their data as well. Oops. So is all of this really big data? Well, let's see. We'll look at the 4 V's of big data. There's velocity, volume, variety, and veracity. So volume is quantity, and right now in the spectrum community, we primarily have gigabytes worth of data, not anything more than that. But as we move toward the streaming data and the sensor data, it's going to rapidly increase. So we know we're going there, and we're trying to prepare for that, basically. In terms of variety, hopefully the previous slide gave you an indication of the different types of data that we have, and it runs the gamut from structured, unstructured, and semi-structured, many different formats to try to digest. Veracity, how uncertain is our data? This is one of the biggest problems with spectrum data. There is a lot of ambiguity both in the structure and in the values. And so this is currently we're beginning to apply rules and metadata tagging to our data. But as time goes on, we're going to look toward machine learning to help make sense of our data and correct it, if you will. Velocity. Currently, we're mostly dealing with static data, and once again, as we get into the collected emission data, our velocity will increase very much. So DoD has an initiative called the Joint Spectrum Data Repository, which is a web application on both CyberNet and NIPRNet that offers access to authoritative DoD spectrum data. It also offers, access to international spectrum data. And there are a variety of interfaces that let you query this data and visualize this data. We have structured queries. We have a content management information system that holds our unstructured data. We have a business intelligence platform, a universal query, which is a kind of an expert query, a business process rules engine, geographic information system. We use cesium, a three-dimensional display. We have engineering services embedded for propagation loss, that kind of thing. And then a REST API for machine-to-machine federation. So for other data sources, we can connect to other data sources and provide data to data consumers. We are currently deployed on MilCloud 1.0, and we'll be migrating to MilCloud 2.0 in probably second quarter FY19. So the JSDR architecture does have some of the sort of the base components of what will be needed for big data handling. We currently have the speed layer through Elasticsearch and MongoDB, the NoSQL database. We have serving layer through Apache Fuse Enterprise Service Bus. We do provide metadata tagging upon ingest using our Pentaho data integration application. Not on this slide, but we do have also the R data analytics platform embedded within JSDR. So we pretty much have the right side of the diagram covered there to deal with static data and, real-time queries of static data. But as we move forward, we know we are going to be looking toward the left-hand side of the diagram, looking toward for data that's going to be, streaming really big data, data that needs post-processing. We'll be looking at something like HDFS, and so that we can do map reduce and all of that. And I should have mentioned that JSDR is primarily COTS and open source integrated together, so we plan to continue that to the degree that we can. So what are some of the questions that we need to answer with our analytics? We have both strategic and operational types of things that we're looking at right now. We are using our business intelligence and analytics platform to look at some strategic planning use cases, including, quantifying DoD equities. May seem simple, but the data resides in different places, and it's hard to get it all together. So, also looking at the impact of spectrum regulatory changes on DoD operations. Historical evaluation of DoD usage, looking at trends and metrics, prediction of interference reports. That's what we're hoping to get to shortly. Identifying data quality issues, predicting future constraints, and identifying acquisition risk. So we are actually looking at systems in the acquisition pipeline right now to try to identify whether any of them are at risk due to regulatory changes in spectrum policy. So we also have operational considerations for our analytics. We really would fully intend, and I believe the efforts of electromagnetic spectrum battle management, EMBM, in the future going forward is going to really look at trying to combine all of this data together, applying business rules and applying machine learning to this, man in the loop, man on the loop, and providing a full-up situational awareness of the spectrum to enable decision making for the warfighter. And just keeping in mind that there are a lot of different spectrum operators, and we need to allow different integrations for them as well, and different views of the same data. So that's all I've got. Rocky?
Are we live? Yes. Thank you, Betsy. So as you've seen, DSO is innovating in the areas of big data, analytics, and sharing. But without an equally innovative visualization capability, the warfighter is going to have a hard time making sense of all these key enablers to make a better informed decision. To help illustrate this point, I was feeling a little bit adventurous last weekend, so I decided to take a little adventure hike in the mountains. So in preparation, I decided to refer to the tried and true 2D visualization tool, otherwise known as a map, to display all the data that I need. However, with a little more research, I uncovered a more advanced 3D visualization tool which displayed the same information in a much more meaningful way and significantly influenced my decision-making process. So I think I'll take a better path. So EMS operators and planners have had to make decisions based on a plethora of data from a multitude of sources, including regulations, engineering analyses, equipment characteristics, frequency assignments, and other information. And all these visualization capability, or a visualization capability, will bring all of this data together in a meaningful way. The right visualization capability can help planners and operators better understand a more complex electromagnetic spectrum environment. So spectrum data visualization is critical to inform our DoD spectrum planning and electromagnetic spectrum, or EMS, command and control decision making. We're experiencing higher demands for spectrum, operating more sophisticated systems in increasingly congested, contested, and constrained environments. And we are facing a more sophisticated adversary. Spectrum visualization capabilities must advance to better inform our EMS planners and operators in the modern EMS maneuver space. We must improve our EMS situational awareness through enhanced modeling and simulation, and the modern EMS environment demands advanced visualization capabilities for the warfighter. So what's our path to innovation? We're beginning with our traditional Spectrum 21 visualizations, which are 2D, coverage plots, spectrum occupancy, and now we've improved our coverage plots from the latest versions of Spectrum 21, moving into today's enhanced capabilities in the Joint Spectrum Data Repository, leveraging Google Earth to provide visualizations including propagation loss, coverage plots, and even LiDAR data. Innovating for tomorrow, we're moving into the use of 3D gaming technology to significantly advance our our spectrum data visualization, line of sight analyses, fly-through coverage plots, and node connectivity diagrams. So, what are we doing? DSO our objective is to improve our DoD strategic and operational spectrum management decision-making through innovative visualization. And to meet this objective, we're currently engaged in two major efforts to explore innovative prototype approaches for visualization of spectrum-related use cases using structured and unstructured data. First, we have a contract through the National Spectrum Consortium to develop a spectrum visualization prototype that leverages innovative 3D gaming technology to display structured and unstructured spectrum data for 5 spectrum-related use cases. Second, we are exploring additional innovative approaches outside of today's conventional techniques through the DoD Rapid Innovation Fund. This effort is just beginning, and it's generated a lot of interest. So to wrap it up, DSO recognizes the need for disruptive technology in the area of spectrum visualization, data visualization, and are actively exploring disruptive technology to improve our EMS situational awareness through enhanced modeling and simulation. We are leveraging commercial industry solutions to explore the art of the possible with the goal of providing improved spectrum data visualization capabilities to support strategic and operational spectrum management decision making. Because it's more than what you see, it's how you visualize it. With that, I'll turn it over to Howard.
So Stuart mentioned the 1755, 1780 megahertz band. That is one of 3 bands that were auctioned off by FCC in 2015 under the auspices of something called Advanced Wireless Services 3, AWS 3. Raised in excess of $40 billion from the mobile broadband providers of service, think Verizon, AT&T, T-Mobile. 1755, 1780 band is currently used for a variety of DoD operations. The raising of that money was contingent upon DoD operations moving out of 1755, 1780 into other bands, including 2025, 2110, which up to a few years ago was an exclusive band for the broadcast auxiliary service. Think the vans that you might see on the side of the road with big dish antenna that the newscasters use. They're talking with towers that might be located talking with base stations that are on top of towers or mountains, etc. And so recent policy changes will enable certain DoD operations to move into that band and share it with the broadcast auxiliary service. One of the key aspects of this new sharing regime, is that while DoD is co-primary with the broadcasters in this band, it is incumbent upon DoD to vacate a frequency if interference occurs. And that's a key distinction in one of the attributes of what we're trying to do here from an innovation perspective, which is op-tempo. Heretofore, sharing with entities other than DoD has been a drawn-out process, weeks if not months, to access a particular frequency. We are currently working on solutions to coordinate access to this band with the broadcasters that still have that time frame in mind, weeks to months. We are looking at techniques to reduce that time frame, to provide greater agility and provide more flexibility in how DoD, as well as the broadcasters, this is part of the deal that the broadcasters and DoD made, is that the solutions that we're coming up with, DoD's coming up with, would also be available to the broadcasters to help with their operations. These are the 4 operations that are slated to go into 2025, 2110. The first, and it's kind of order of complexity. The first is a ground-based point-to-point microwave tactical radio relay. The next is command and control links for small UAS operations that are flying at relatively low to mid altitudes. The next is high-resolution video that are on rotary aircraft. And probably the most complex one we're going to have to deal with in the sharing regime is the targeting tactical networking technology, which is a wideband system that's on high-flying air-breathing platforms. So we are also using the National Spectrum Consortium, which is a consortium of non-traditional contractors, academia, et cetera, to help bring innovation to the spectrum sharing space. And you can see some of the attributes at the bottom there that we are asking the National Spectrum Consortium to address. And all those can be summarized in those greater op-tempo, greater agility, and greater flexibility in terms of how DoD uses the band. We're also looking at leveraging the solutions that the NSC is coming up with to do other things in other bands, and not just the use case here for 2025. So what I have here is a spectrum sharing framework, if you will. To the far left is a highly centralized way to share spectrum, which is generally database driven. If you're familiar with the TV whitespace approach to spectrum access, it's analogous to that, where the spectrum decisions are made centrally within a database, and those decisions are broadcast through the network and ultimately operated on by the spectrum-dependent device that's actually accessing the spectrum. To the other extreme is where those spectrum-dependent devices are making those decisions on their own. And let's see, is this a pointer? So the circles there, moving up from the bottom left to the lower right, represent where those spectrum access decisions are being made. So far left, highly centralized, are being made within a database. Far right, highly decentralized, being made by the spectrum-dependent device itself. And across the top there, you can see the 4 projects that we have ongoing with the NSC. And it's a nice distribution of how spectrum access, spectrum sharing technologies, concepts could be applied to spectrum sharing in general. For this use case, it's 2025. What other points I want to make here? I think I'll leave it at that, Bob.
Okay. Thanks, everybody. So with that, we'll go ahead and open it up for questions. It looks like we've got almost 20 minutes for questions from the audience. So if you have a question, please step forward to the microphone. And anybody?
As you think about direct line-of-sight wireless for U.S. military purposes, like, for example, a U.S. Navy ship pulling into port, both North America and then overseas as well, how do you deconflict spectrum sharing for platforms that deploy and then have to use allied spectrum and that sort of thing?
Thanks. That's a great question because it kind of evokes both a domestic flavor and then an international flavor. So let me use 3.5 gigahertz first as an example. It's very similar to what you described, but for Navy microwave read radars. And in the case of 3.5 gigahertz, it is incumbent on the mobile operators to detect whether or not the DoD is using that spectrum, and then they then maneuver out of the way, if you will, of that radar signal. Now that's on paper seems to work. We are in the implementation stages now, and there's a great deal of confidence building measures that have to be done to make sure that ecosystem will behave the way we think it will behave. That becomes very, very complicated when you go overseas, right? So so getting international norms that that can transcend those boundaries and assure that that same Navy ship has that same access to spectrum as it goes over for peacetime or wartime operations becomes more challenging and could be licensed for other kind of more nefarious things. Like so many other things, it depends on standards and international norms in terms of the behavior of those standards, and we know we can't count on that in all cases. And so taking those kinds of spectrum sharing systems that are bolt-on and expanding those to international scenarios becomes challenging. There's certainly a cyber dimension to that. There's certainly bad actor dimensions to that have to be fully considered. And then I think that problem gets worse as you go from bolt-on, clock scales to machine-based type of time scales where things might happen so fast that you don't even see it. And that is something that has to be fully kind of thought through. Okay, so one.
I think the formal process for the Navy is to do like a host nation agreement.
I was just going to say, one other thing I think to address is the flip side where on the international side, we have to account for their spectrum use and the policy, sort of that policy implementation that says, hey, our systems are going to automatically adjust. So if they're going into a foreign port where they are unable to radiate any of their devices, they know that in advance. It's built into the system.
Right.
So it's sort of a fail-safe. Right now, it's a manual process. What port am I going into? What's the host nation approval status there?
Mm-hmm.
And then adjusting the radiation accordingly. So.
Right, and then the interference detection and resolution dimension to that goes along with that kind of manual-based process.
And my follow-up question was that the host nation agreement process is somewhat cumbersome. Do you think in the future that we might evolve to some global standard where we can operate, I guess you really can't do that with adversaries, but maybe with our nations that we're allied with, perhaps with NATO?
My personal opinion, I think the technologies, dynamic spectrum access, for instance, those techniques, policy-based techniques, could allow maybe a host nation process that looks very familiar to us, but maybe happens much, much quicker.
Okay, that's great. Thank you.
And we had another question here.
This touches on both the big data and some of the, I'll call it, autonomous frequency selection. I work at a university. We're doing some neat experiments, and just a few guys. This is involving drones. So if you had an idea for sensors, big data input, and I call it autonomous frequency, autonomous automatic link establishment, where it goes ahead, the devices control their destiny. Let's put it that way. Are there any kind of experiments or any type of information you guys would like in that domain? I've got all these wonderful PhD and graduate students. I've got to give them something to do. Thank you.
So, a great question. I think it would be great to have a conversation with you afterwards to follow up in that area. We're very interested in what academia is doing in this area. We're working very closely with all of the DoD labs as well as DARPA to understand how they are innovating in the spectrum area. For example, DARPA has a Spectrum Grand Challenge right now. One of the few grand challenges that DARPA's had. And they are looking very much at how do you both collaborate and cooperate in the electromagnetic spectrum to get your information through. So we're looking for innovation across the board wherever it is. So. Next question. Thanks.
So how do you see this DSO innovation actually getting transitioned to the tactical edge?
So great question. I think it's going to be in bits and pieces. And I'll take some of the work, for example, that we're doing with 3D visualization. Clearly, a disruptive type of technology. We're going to have to prove that out. We're going to have to mature it. But we have opportunities as that technology gets more mature to field that in capabilities that such as JSDR, which is part of the GEMSIS program. So I think there are opportunities as the GEMSIS program moves into future increments for us to roll out those types of technologies. There's also the opportunity to offer those technologies to the services. The services have their own capabilities for how they manage spectrum, and in the future will command and control spectrum. So we don't have to do it all from DISA's standpoint. We can offer those capabilities to the services.
And if I can add, Betsy touched on this, but one of the things that makes this a real interesting and quite frankly a real fun space is that we have everything from 5 to 6 year decision cycles all the way down to 24, 48, 72 hour decision cycles, and so understanding the information needs as you go from a generating force or a strategic planning type of environment down to the tactical edge, and understanding how the information consumption behaviors change with the cognitive abilities of the users and the time scales on which decisions have to be made. I think that's all part of understanding how much of this can proceed downrange to echelons above. I'm dropping back to the Army terminology now, but division level, brigade level, battalion level, that sort of thing.
So algorithms, big data. Of course, big data's got its analytics. So it occurred to me that there's kind of somewhere down the line some fusion of those activities. I would suspect. You briefed independently on algorithms and big data, but can you talk, how you're looking into the future, how those things can be integrated together?
Yeah. So right now, in our algorithm development, we have both the effort I mentioned for doing aggregate interference. We also have work going on looking into applying optimization algorithms to the spectrum allocation problem. And so, how do you assign frequencies to different systems in a way that uses the spectrum in the best way for some measure of what's best. And so big data, the data is critical. The better your data is, the more data you have, you can apply those optimization algorithms over it and get to better solutions. So what Betsy is building with the JSDR is kind of that foundational layer on which we can build our optimization algorithms and get those better solutions. The aggregate interference is in many ways kind of the same. The more data you have, the more different measurement we're collecting a lot of measurement data as well with that to improve our models. There's a lot of data there. So how do you go through that data? How do you find what's normal, what's not normal in that measurement data, build your models from there. So that's kind of where some of the touch points are between the algorithm development and the big data work.
So I'm also with the DSO. In one way, I mean, these folks are a lot smarter than I am about spectrum, but I've had the opportunity and some working with folks in the audience here over the years of how do we effectively optimize the resource that's available to us. And if you look back, through IT history, we went from circuit switch to packet switch to IP. We went from dedicated SATCOM links to shared SATCOM links. We went from physical CPUs to virtual CPUs, and now in the cloud environment. This is the logical next frontier of how do we optimize the RF resource that we have. We have environmental factors, we have contention, but really the bottom line is how do we accommodate that contention and how do we demonstrate agility where we can shift frequencies when necessary, near machine speed as mentioned, real time. So anyway, just leave you with that thought as well as three letters, SDS. Everything we do, you heard it, spectrum dependent system. We need to pay attention. Thanks.
Thank you, Alan. So any other questions from the audience? Okay. Go ahead, sir.
Bob, you alluded to it, Mark Kilcawley of the EBI Management Group. I want to hear about the business aspect. You said our mission partners currently have this requirement and need. Does DISA see in this becoming like a reimbursable service where they can grow this, okay, and collect the requirements and provide those requirements at greater efficiencies using economies of scales? Where do you see DSO in this service going forward on the business side?
So great question. Honestly, that is not something that we have thought about, growing it as a service that we provide across the board. I suppose that that is something that could be looked at. But I'll tell you, honestly, the services are very involved in today's spectrum management, the future of electromagnetic battle management. They're very engaged. And so we work together very, very closely with our counterparts in the services to bring it all together and to provide services of common concern, capabilities such as JSDR, capabilities to manage the spectrum such as Spectrum 21. And so we collaborate with them in every way possible, as opposed to offloading all of that work to DISA. But certainly something to think about as potentially an improvement of efficiencies in the future. Okay. So if there are no other questions, anybody? Okay. If there's no other questions, I'll remind everybody that continuing education unit credits are available for this session. So if you want to get credit, have your badge scanned in the back by Gary Webb. Gary, could you stand up? Just see Gary, have him scan your badge, and you'll get an hour credit for this. And thank you, everybody, for
Thank you very much.
for participating. Thanks. Great questions.